critical question in inferential statistics is determining the degree to which sample statistics vary from each other and from the population parameter. Consider whether the mean weight from a sample of 10 Houston women would equal the mean weight of all women in Houston. Think about how you would answer this question. You would not expect your sample mean to be exactly equal to the mean of all women in Houston. It might be somewhat lower or somewhat higher, but not exactly the same. Because inferential statistics concern generalizing from a sample to a population, it is critical to determine how far sample statistics vary from each other and from population parameters. These determinations are made based on sampling distributions. To illustrate the concept of a sampling distribution, we'll use a simple example. Select two of these three pool balls randomly and find the average of their numbers. When you consider all possible outcomes from this scenario, you will find that all the means are either 1.0, 1.5, 2.0, 2.5, or 3.0. Notice that some means occur more frequently than others. For example, there are 3 ways to get a mean of 2, but only one way to get a mean of 3. The frequencies and relative frequencies of each possible mean are reported in this table. Because there are 9 possible outcomes, the relative frequencies are equal to the frequencies divided by 9. This graph illustrates the distribution of the relative frequencies. Since the y-axis is the probability of obtaining a given mean from a sample of 2 balls, the distribution can also be considered a probability distribution. This distribution is called the sampling distribution of the mean. More specifically, it is a sampling distribution of the mean for a sample size of 2. In this example, the distribution of pool balls and the sampling distribution are both discrete distributions. In other words, the pool balls can only be 1, 2, or 3, and the sample mean is necessarily one of 5 values. There is an alternative way of conceptualizing a sample distribution that will be useful for more complex distributions. This time, we're going to use multiple samples. Imagine that 2 balls are sampled with replacement, and the mean of the 2 balls is computed. This process is repeated for thousands of other samples. A relative frequency distribution is drawn for the entire set of means. The more samples, the closer the relative frequency distribution will come to the sampling distribution. In other words, you can conceive of a sampling distribution as being a frequency distribution based on a very large number of samples. To be strictly correct, the sampling distribution only equals the frequency distribution exactly when there is an infinite number of samples. It's important to keep in mind that every statistic, not just the mean, has a sampling distribution. This table shows all the possible outcomes for the range of 2 numbers. This table lists the frequencies of each range. This graph illustrates the sampling distribution of the range for this discrete distribution. It's also important to keep in mind that there is a sampling distribution for various sample sizes. For simplicity, we have been using a sample size of 2. This graph illustrates the sampling distribution of the range for a sample size of 3. Now it's time to move beyond our discrete set of 3 pool balls. Instead of using 3, let's use 1,000 pool balls with numbers ranging from 0.001 to 1.00 in equal steps. Though this is not actually continuous, it's close enough for practical purposes. As before, we're interested in the distribution of means that we would get if we sampled 2 balls and computed the means. In the previous examples, we started by computing the mean for each of the 9 possible outcomes. In this case, we would have 1 million possible outcomes. It sounds like it would be very tedious. Instead, we can use our second conceptualization of sampling distributions. Specifically, we use the relative frequency distribution that would occur if samples of two balls were repeatedly taken and the mean of each sample computed. As we stated at the beginning of this section, sampling distributions are important for inferential statistics. In the examples given so far, a population was specified and the sampling distribution of the mean and range were determined. In practice, the process proceeds the other way. You collect sample data, and from these data, you estimate parameters for the sampling distribution. This knowledge can be very useful. For example, knowing the degree to which sample means differ from each other and from the population mean gives you a sense of how close your particular sample mean is likely to be to the population mean. Fortunately, this information is directly available from the sampling distribution. The most common measure of how much sample means differ from each other is the standard error of the mean. The standard error of the mean is the standard deviation of the sampling distribution of the mean. If all the sample means were very close to the population mean, and to each other, then the standard error of the mean would be small. On the other hand, if the sample means varied considerably, then the standard error of the mean would be large. To be specific, assume that your sample mean is 125 and that you estimate your standard error to be 5, using methods to be described in a later section. If you have a normal distribution, then you could be pretty sure that your population mean is between 115 and 135, since most of a normal distribution is within 2 standard deviations of the mean. To review, there are 3 primary ideas to remember from this section. First, sampling distributions help determine how sample statistics vary from population parameters and other sample statistics. Second, as the number of samples approaches infinity, the relative frequency distribution approaches the sampling distribution. And last, keep in mind that all statistics, not just the mean, have sampling distributions. In later sections, we'll be discussing the sampling distribution of the difference between means and the sampling distribution of Pearson's correlation, among others. We hope that you now have a sense of the concept of a sampling distribution and its potential uses.